Many of you were, or some of you at least, were at Rick's talk yesterday, and Marcin Linehan gave a very nice introduction. And I think if you look at a linear description of Rick's career, couldn't help but be impressed. He got his undergraduate degree at Yale, MD at Duke, did his medical internship and residency at Mass General Hospital, and then came to the NIH, where he was a research associate at the NCI and what was then called NIADDK. And at age 33, he became the youngest branch chief ever at the NIH, became chief of the cell biology and metabolism branch in the Child Health Institute. And no one has broken that record yet. And given that we normally require that people be at least 50 before they achieve tenure now at the NIH, it's not likely that anyone will come close. 11 years later, at a pretty young age, he became director of the National Cancer Institute. And then after his term here, left the NIH to become executive director for global health programs at the Bill and Melinda Gates Foundation. And for the last 5 years, he's been managing director of the Column Group, and as many interesting ways to bear on advances in translational research. Now, that's a kind of linear description, and it's obviously very impressive, but it does miss some essential elements of Dr. Klausner's career as an innovator, an advisor, and a revolutionary for the way we do research. And Rick told me yesterday that this career began in the 3rd grade when his teacher noted on his report card that he would either win a Nobel Prize or be hanged. And he's been working towards both ever since. When he was, I remember this very well, after he finished his internship and residency, he actually wrote a textbook of medicine that would be useful for interns, so that book would demystify medicine for them, and turned out to be a wonderful adjunct to the training that young physicians have in this country. He's been very supportive of global health efforts in everything he's done at all levels. And obviously, the Gates Foundation work was a direct manifestation of that interest, but in all other matters, he's been involved in global health, including diplomatic efforts. He's advised most of the major biomedical research foundations in the country, and has been advisor on issues of diplomacy to the U.S. State Department, the governments of Norway and India. His scientific contributions, including the elucidation of how iron regulates its own metabolism, and the pathway for T-cell receptor activation, and co-discovery of the von Hippel-Lindau familial gene that is involved in kidney cancer, has been recognized by quite a number of awards, including obviously membership in the Institute of Medicine and the National Academy of Sciences, and many, many other awards, including a huge list of named lectures. So we're fortunate to get him here without naming the lecture. Although it is the Wednesday afternoon lecture, yeah. Now, many of us have had a chance over the last day or so to interact with Rick, and it's really been delightful to draw from his energy, his enthusiasm, and his insight into complex scientific and policy issues. His talk today is entitled "The Challenges of Bringing Omics to the Clinics, Lessons for Molecular Diagnostics." Let's welcome a creative scientist, a charismatic leader, advisor to presidents, prime ministers, and kings, and an innovative entrepreneur, Rick Klausner.
Well, thank you very much. I'm not sure what to say after that. Other than maybe, at the end, tell some good stories, and particularly about Michael. I want to talk about molecular diagnostics, and I want to go back to 1995, which was a quite exciting time. It wasn't the only exciting time, but it was an exciting time to think about molecular diagnostics, and particularly in cancer. This is a slide I think I got from, I'm not actually sure where I got it from, now that who did I get this from? I don't know. It's from Stanford, I think. But I used it in 1996 at the NCI appropriation hearings. With a vision, not that it was my vision, but a vision that we were all having with this emergence of the ability to measure in a way that we never had before biologic information. The emergence of even talking about aspects of, quote, systems biology, which very much involve the ability to systematically measure. The idea that we would add to hypothesis testing research, this sort of hypothesis generating data collection. And at the time, many of us were quite taken with the possibilities. And particularly, again, in cancer, with the possibility and promise that 100 years of classifying, diagnosing the name of your cancer would be transformed, as shown here. We would, this would be the image, and we would learn how to discern it. And there was a lot to recommend the possibilities here. What I want to talk to you about is how hard that's been. And I want to use a case example of what is, to date, the only FDA-approved high-dimensionality data, high-dimensionality measurement system for diagnosis, and to try to go through lessons learned, why this has been so hard. Actually, the personal part of this, was about 5 years ago. I got a phone call from the editor of Nature, and I was told that, quote, they called me Dr. Clauster, which is unusual. It's because I didn't know the person. Said, we've been reading things that you wrote, speeches you gave, starting about 10 years ago at NCI about the transformation of molecular diagnostics. And, I'm assuming they're going to make a special issue with my picture on it, and, or statue or something like that. And so I was ready for that. His next question was, and as far as we can tell, it's had no impact on the practice of oncology, and would you be willing to write a review on what went wrong? The idea of writing a sort of, it felt like a mea culpa, So in some sense, that reignited the journey I'm going to tell you about. There was, I don't remember when we did this, but at the end, in 1995, one of the first groups that I invited to come to NCI of many working groups that were tremendously fun and really just fantastic was something called the Molecular Diagnostics Working Group. It was so much fun they would never disband themselves. They just kept going. And they were incredibly helpful, great group of people, incredibly helpful at helping formulate whole new programs and approaches to try to capture a lot of this sort of omics and emerging genomics that we were now beginning to see on the horizon, as we assumed at the time. We were still hopeful that there was going to be a successful human genome sequence. There was. And these new technologies. And there were many initiatives out of that, but one was called the Director's Challenge. And the challenge was to ask people to use a variety of new measurement technologies with the goal of creating new classifications and diagnostics of cancer. Just before it was released, the executive committee was meeting, and we decided to add some money for what we thought was the low-hanging fruit problem that this ought to solve really easily, and this would be the quickest, sort of movement to the clinic, and that is to use, molecular expression, gene expression, to define tissue of origin, and hopefully to solve the problem of a cancer of unknown primary, which is not incredibly uncommon. And in fact, it may be much more common if we're not right about what our diagnosis is, which I'm going to come to. So this was the low-hanging fruit. And we had this feeling, out of our naivete, that if you couldn't do that, it was going to be hard to do anything more complicated. Well, I say all this because, in fact, as Nature pointed out, at least quickly, there wasn't anything that was on the market that was changing how the practice of oncology was done. It's not that people weren't doing this. People were looking at gene expression arrays in various places, like for lymphoma. I don't know if Lou is here. But the reality is it was really hard. It was incredibly hard to translate this. So why? So what does it take to get genomics into clinical lab? And what I mean by genomics is this sort of these types of data sets. Well, one is to do it and have people want to use it. It's actually got to be useful. Not just interesting, but it actually has to, there's something about what the information you get, you have to be able to not only rely on and believe that the information is right, but it has to be meaningful. Is it going to change anything clinically? And that's actually, when you really get down to it, is limited by lots of things, like what are the choices we have, even if you knew differences. What turned out to be, I believe, an overwhelming challenge that was much harder than I think a lot of us realized, particularly those of us who were mathematically naive, was the analytic challenges. And in fact, I will tell you about one of the last meetings that I remember being at of the Molecular Diagnostics Working Group, where we brought in mathematicians from a variety of places who had been working on this issue of high-dimensional data sets, and got up halfway through and basically said, what are you guys talking about? We've been working on this for 100 years. You actually can't do this. This is a well-known problem of signal to, this was, I don't know if you, Dina, you were there, you remember that, but it was really pretty striking, particularly Eric Lander, who was up at the time showing us, how to do it. And, maybe that was an exaggeration, but it's a huge challenge, what they call the deal with the end problem. And that is, how do you truly distinguish signal from noise as your dimensionality of your data set over the number of measurements, the number of samples we can look at, gets higher than, as they pointed out, much higher than 10 to 100, no less thousands to tens of thousands. Novel methods for distinguishing signal to noise had to be established, and it had to be established on truly robust measurements. And this is to make sure you can translate this to the reliability and performance characteristics that you need for a diagnostic. And you needed ways, and this was a huge mathematical problem, to truly normalize your data. To normalize data across different platforms, different data sets. We all talked about this. But this is, again, was much bigger challenge to actually get than, I'll just say that certainly I realized. And then, of course, there is this very challenging problem of adapting research tools to the level of standardization, reproducibility, performance between labs, within labs, cross labs, working with heterogeneous tissue, figuring out how do you deal with heterogeneity, how do you deal with percentage of tumor, how do you develop robust and effective data quality control processes, how do you make this work in samples that are really there, like not frozen tissue, because turns out there ain't much of that out there. You need to make this work in paraffin-embedded formalin fixed tissue. So there were an enormous number of just pragmatic problems in translation. So, in fact, mathematicians and lately, really, machine language people have really been exploring the issue that is comparable to I think, hypothesis testing versus hypothesis generating. And they actually talk about, in essence, this distinction as they try to apply it to biology of diagnostics versus therapeutics, predictive versus explanatory. And that's what the distinction, and for clinical diagnostics, you can get a long way with understanding nothing if you have really robust predictions. For drug discovery, in reality, as we've discovered, that's really hard. That without explanation, that's what we were talking about yesterday, about translatable science, it is very difficult. They are not one and the same, and approaching them mathematically is not one and the same. And I don't know enough to defend what I'm going to tell you, but I'm told that what I'm going to tell you is true, that while you can apply the types of statistical methodologies that we've all gotten comfortable with that lead to p-values and things like that for testing hypotheses statistically, actually with these sorts of enormous data sets and discovering patterns that are really robust, that you can really demonstrate are patterns that are distinguishable from the random patterns you always get in high-dimensional data sets, our statistical methodologies actually are not well suited to them, even though I will say, this is part of my being provocative, that essentially all of the publications using this use statistical methods, and we report, to be honest, we'll say this, ridiculous p-values, which we feel good about, but it's not clear what they mean. And so what are mathematicians doing about this? How are they dealing with this? So in that world, this sort of dichotomy, the prediction-explanation dichotomy, is really well understood. And I'll just speak for myself. It certainly wasn't well appreciated by me, and I'm sure I'm representative. And as a result, what you see, and what most of our publications about, not that there's not interesting stuff that gets generated. That's fine. It's a very different thing when you get an interesting insight that leads you to do something from translating that into a robust predictor. And yet, in fact, both tend to use and tend to look for the minimizing number of relevant, meaningful, therefore predictive, and statistically assessed variables. However, as has been seen in many fields, that statistical approach does not generate mathematically optimal predictive models. Just to put this in perspective, gravity, we're really good at predicting, with real precision, gravity, or some people are. But unless Michael's son has done something recent, the deep explanation isn't there. Another example is we have really a good explanation of earthquakes. We have a very good explanation. And our ability to predict is basically, very minimal. And there's lots of examples. But the power of prediction without explanation is very striking. And I'm hoping, this is really what I'm trying to achieve, I'm hoping I'm the first person in the Lipset Auditorium to talk about Ptolemy's heavenly mechanics. I wonder if the NIH Catalyst will check that out. That's really the one thing, Michael, I wanted to achieve. But, it was a remarkably good predictive descriptor of the movement of celestial bodies. It was completely wrong. And it took about 15 centuries to come up with the correct explanation, which required at least 7 site visits in between to continue to be funded. Okay, so useful predictions. How do you get them? So an alternative approach, if we're going to really get robust predictions, is to decouple predicting behavior from understanding it. And that was this idea of, it's different than a hypothesis generated because we were looking for an entree into explanation. The question is, how far can we push useful predictive approaches? And the bottom line is that the way to optimally do that requires something we didn't have access to in 95 and everything, and that is incredibly high capacity computing that the cloud has given us. And the breakthrough I'm going to talk about could not have happened, the single example, without using cloud computing, because it was just, and I'll show you what it would have taken, like on your computer. But what has been found again and again, which is really nice for the D over N problem, is that if you can do that sort of computing with the right modeling and the right machine learning models, and I'll talk about that a little bit, is that in fact optimal models aren't about minimizing the number of useful variables, but just the opposite. It's involving as many as possible, and I'll show you sort of a counterintuitive test of this in a real application. And of course, you always want to be able to, to teach your models, and so having models that are amenable to the input of insight and explanation is if this sort of process is going to be useful and last over time and continue to get more useful is another aspect of the fundamental design. So, these are some of the and the optimal analytic techniques turns out is not statistics. If this is if you're going pure prediction, but it is much more amenable to learning, modeling comparisons, and there are different skill sets, and there's all sorts of reasons, and it's only recently, and it's a very interesting thing what cloud computing has done to the ability to actually address these sorts of things if you don't have huge supercomputers. The potential applications, if you can do this, of course, are all the obvious ones, just the types of things we imagined, 10, 15, 20 years ago. Okay. So now let me give you an example, the example I'm talking about. And let me first, because I have to do a disclaimer, it's from a company that I put together. I sort of discovered the group of mathematicians. I'll tell you about that group. And then I didn't invest in it, but I actually just convinced other people that this was a company that needed to be formed, but I am on the board and do own stock. So you should discount everything I say. And I have no interest in any of you buying anything, okay? I'm just using it as the only example I know, and it is the only FDA-approved example of this. So to put the pieces together, to actually make a diagnostic, as I said, there has to be clinical utility. There really needs to be robust analytics, and you have to define robust. What is performance that actually could make you decide that an individual patient is really in a particular group or has a particular answer or not? What's the probability that you're wrong? You put them in the wrong group. There needs to be reliable systems, and that's all about, you only get there with reproducibility and standardization. So the clinically meaningful question was our low-hanging fruit. So, just to put this back to this personal story, I agreed to write this article for Nature, What Went Wrong, and decided that I would call everyone I knew to make sure I hadn't missed anything and that something hadn't suddenly gone right, which I can get out of writing the article. And I never did write the article, but I came across a little company that had spun out of Stanford, and these were engineers and mathematicians. One particular mathematician from Serbia, Ljubomir Butarović, and these people knew, and really, and still, as far as I can tell, know nothing about biology and even less about cancer. But this was the amazing thing. They were following the director's challenge. They were reading about it, they were looking at things, and they decided to work on tumor of unknown origin. people, I mean, and I remember after working with them for a few years, Luberman asked me, he says, I'd love to actually see what a cancer cell looks like or something, because, and maybe that was really important. They were just, he was from a totally different world. Now, they showed me what they had done, and because this was an area I was very interested in, I was looking at lots of solutions people were proposing, and I'd come up with my own, maybe useless, diagnostic kit about when things worked or not, such as when you looked at AUC curves and asked the question, when you did this whole analysis, and then you asked, how did the contribution of how many variables to the answer you're getting, how did that distribute? And again, you would find one strange fragment of thyroglobulin was 90% of the AUC, and it's just, and there were all sorts of things. Or that the more samples you got more heterogeneity rather than converging on, homogeneity. And there were a whole bunch of little things. And all I can say is all those diagnostics that I didn't know if they were useful or not, but I was using, they had beautiful data in ways that I had never seen. Now, I was still at the time was working at the Gates Foundation, so I took this, this guy's work over to Mr. Gates and said, you must have some really great machine learning people over at Microsoft. Would you connect me? And they went through it and everything like that. And I must say, they were incredibly impressed and actually are using this. Some breakthroughs this guy made about how to do machine learning-based search models, and also how to do normalization, which was used. So you can actually normalize across data sets, what is an actual number. And so you can compare data sets. Okay, so that's the story, so, and my disclaimer of conflict of interest. The clinically meaningful question was CUP. The company actually recently did a Medicare study, and in Medicare, in 1 year, there were 53,000 new cases of CUP. Our estimate is, 70 to 100,000. It's actually very interesting to look at a year of Medicare, because what you find is a single patient is diagnosed as CUP, and then later as something else, and then again as CUP. And it fits with treatment change. I mean, it's a very interesting thing, of course, to analyze Medicare databases about that. There's CUP per se. It's very frustrating. It's very expensive. The average cost of the workup to try to get a diagnosis is $18,000 in the Medicare database per patient. You delay treatment. Now, there's a oncologic nihilism, so what? These are metastatic cancers. I will show you examples, or I'm not sure I have an example, but where 52-year-old man treated for lung cancer, nothing says this is testicular cancer. I will show you the tumor, I don't know if I have it I can't remember what I have in the deck, but anyway, testicular cancer responds nicely. These are anecdotes, but I'm going to show you a compilation of the experience, and it's really quite surprising. So, I think the nihilism is saying, do we actually care what a tumor is when it's metastatic? I personally, I'll just say it's my editorial thing. I think it's unacceptable. And becomes more and more unacceptable as we do actually get better therapies, even if they're not molecularly targeted therapies, but better standard of care therapies. So there's a reason to do this, but I actually think there's a bigger reason than we thought. And the bigger reason, of course, is what's the difference between unknown and uncertain? How do we know when a metastatic cancer is called ovarian cancer? What is the basis for our level of certainty about that? And that's data I'm going to show you, which is a big surprise in practice. Okay. Now, I won't go through this. First of all, how does one define a cell lineage? Well, I do think the best definition we have for a cell lineage, a cell type, is defined by a particular pattern of gene expression. So, in fact, looking at lineage-specific gene expression patterns is a very biologically, I think, defensible approach. Underneath that, whether you want to look at epigenetic marks or things, there's also things. But in fact, I don't know that there's anything to suggest biologically that this would not be a working definition of of a differentiation state, the pattern of gene expression. These are two different cancers, one side versus the other side, clear cell, renal cell carcinoma and ovarian, and, I don't know which is which, but you can't tell. There's a lot of that. Immunohistochemistry, I think, is really a fascinating phenomenon. Besides only measuring time, and not all proteins have useful antibodies, the staining is incredibly qualitative. Reading is very subjective, and this has been measured, how irreproducible it is across readers. But in fact, there's been essentially no published standardization of IHCs. And there has been, for almost no IHC, any rigorous validation of performance. You ask the FDA about that, it's very clear. None of those would be approved now. This is all pre-clear, but certainly pre the FDA deciding that they are going to be arbiters of these sorts of molecular diagnostics. There's just, you cannot find in literature. And in one study, I'll show you sort of a case study that we're looking at, in 100 cases, over 150 different antibodies and different antigens were reported for patients. And the vast majority, in fact, none of them have what anyone would call validation studies. We don't know the performance, but that's the standard. So that's where we're starting from. It's not the only way that you make diagnoses, of course. There's lots of information you put together to determine the site of origin. So the company is called Pathwork, and their goal was to do this by what we thought we were going to do in 1995, using transcripts. They looked at lots of platforms and decided to use an AFI gene chip, a 22,000 gene array. It's now been custom made, but it doesn't really matter. And to use the type of informatics I've been talking about that required both cloud computing and this new modification of machine learning. The key was to collect and analyze very large training sets of tumor samples, over 5,000 were done, assuring that those training sets were both highly diverse, but also can be separately analyzed. And it turns out there's virtually no change in tissue-specific lineage patterns as a function of primary, metastatic, well-differentiated, or completely undifferentiated. That's sort of nice. 58 different morphologies got tested that way, and the current test has 15 different sites that make up about 90% of all cancers, and a new version will come out that will get that up to 98%. And it works, what I'm going to show you, on a single microtome slice of formalin-fixed, paraffin-embedded tissue. And because of this informatics and normalizations, we can also do it on things like CTCs and get a gorgeous signal at as little as 5 cells of the RNA pattern, and can tell where the CTC, what sort of tumor it comes from. So the classification algorithm, I just told you about that. About 22,000 transcripts are measured. Those are the variables. There are 15 to 20 classes that go into the model building, and the method of choice for that is a support vector machine classifier, and that comes from extensive experience in machine learning, literature reports, and very critical is it gives you an entree into one of the biggest problems with going from learning sets to validation sets, which is overfitting of the data, and I'll talk about that a little bit. So here's what the model, sort of the complexity of the model, I'm not going to go through it. You do 10-fold cross-validations against 10 distinct model experiments or partitionings. There's what's called a 5 by 50 grid that you have to do with 200 pairwise models, which means 5 million models for typical run on a typical standard CPU core. That would mean it would take 1 minute to run one model, and a run requires a minimum of 5 million models. And this is why it's just not doable. If you want to if you didn't have the cloud computing or something like that, but you wanted to use a MATLAB package, you can use a MATLAB package. You just can't do all these things because it's going to take you longer than you would want before you publish. The fact is, this 5 million models in a run becomes the tip of the iceberg the way you do this, because you then have to do this whole process of data normalization using, it just gets very complicated. And what it turns out is it's the equivalent of about 100 million models per run. Okay, so you can, so it's more than 9 years. So, and I just say this because, I don't know how much you all talk about the potential impact of these transformational computing things. I mean, cloud computing has really fundamentally changed the types of things we can imagine doing. And the test and the results that I'm going to show you and their performance, we just couldn't get. We tried it with MATLAB or anything. You just can't get it. And I'll show you the difference between the performance characteristics, and they are the difference between, in essence, the level of uncertainty that would not make a useful clinical test and a level of false positives, false negatives that does make a useful clinical test. So one of the interesting things in this is that the implication of this model is what you look for is a model where in this case, your ability to predict the tissue of origin and there are two curves. Oh, no. Oh, yeah. Two curves here. One, where you do the model, and one, I forget which one, is you remove the most informative 200 genes and then rerun it. And it turns out you converge in all cases on the same data. And that's really, again, a fundamental difference about when you're wanting to optimize a purely predictive, totally dumb, no insight model. That's what you want to look for, and it's very different than what most of the classifications that that are out there, but don't have the performance to become a clinical test. Okay, I'm not going to go through that. The standardization algorithm was absolutely critical, and this again was a machine learning thing. How do you find, it's like the problem that was critical in astronomy of finding, constant intensity stars. How do you figure out what is, where do you get your point of departure for standardization? And basically, it took this type of computing to find 29 invariant genes that we've looked at the names of all of them. They don't I certainly wouldn't have called them housekeeping or not housekeeping. I mean, I would have no idea what to call them. It's sort of interesting, and that's turned out to be incredibly important. To normalize expression. And normalization of expression across data sets actually is really a big deal in robustness and reliability. And before this, we actually couldn't do it. And this is not the only example. There are other people that have worked on solving these normalization problems. But just to give you some examples of a measure of actual mathematical normalization, as you look at the kappa factors, across sites of measuring, say, a clinically used IHCs, and these are considered really poor performance until you're above about 75 to 80. And when you do, what Pathwork can now do, you really get numbers like around 80 to actually more like 90 plus. And the current version is closer to 0.95. FISH is actually pretty good. And this is what happens. If you take the standard mass normalized expression, this Mass-5, which is the most common normalization for like a gene chip expression, this is what you get as your correlation coefficients. And the correlation coefficients, although I actually can't give you the right number, relate to sort of what ends up being false positives and false negatives, and they're very high. And then when we take the same data and use this type of machine learning standardization, what we end up getting to is this. And and this is sort of in some sense, the bottom line of this. This becomes the difference between a level of predictability and robustness of, very high negative, incredibly high negative predictive value, and quite high, as I'll show you, positive predictive value. And we can take other data sets. We've done this like with the GHI, Oncotype DX, and really recreate it, and the performance goes way up. But although that's a data set that is about cherry picking a small number of variables, and it's very smart. I mean, I think it's it's one of the best examples of that. But it's trying to mix the statistics of explanation with prediction, and it's why there's so much enormous uncertainty. Okay, so you get profiles, and this is what a readout looks like when a doc orders this, and basically you get from this real numbers, and these are real probabilities, and you can say what is the probability that it is and it isn't, and you get of course at the same time, which you can't get from IHC, unless you get the level of rule out of all of those, and then this happened to be colorectal. No, they don't all look this perfect, but most of them look really, really clean. It's really, really striking. This was an example of a metastatic neck mass being treated, and this was sent around to 4 labs to see if this is robust and everything, and you can see the answer. And this was negative for the standard thyroid markers, but it was clearly thyroid as a tissue of origin. But this was point to show how robust this is as a result across labs. And these were done completely independently. It's not just data files. This was full starting from the paraffin section. In the early days, there was, the data we had was about 91% overall agreement, metastatic tumors, with when we actually knew the site. There was really not any significant drop if you got to undifferentiated or poorly differentiated, and there was no real difference between primaries and mets. This has gotten much better. The non-agreement, what I will tell you is that the majority of these, and now going back and finding them, were that the diagnosis was wrong. The starting diagnosis was wrong, but that's how you have to do that to do a kosher data set. So test performance. We wanted to see whether, sort of end stage workup of CUP, where it's been through multiple places. This happened to be finally gotten to the Mayo Clinic or University of Pittsburgh, and enormous number of studies were done. So this is all pre-morbid. And just the answer, what do these undiagnosable CUPs, what does their tissue of origin look like? Are these all weird things? Are these all, very, very, can you not find their tissue of origin? And in this first study, and we've done it again, about, for this panel, 75 to 80% are just very clearly actually common tumors. That's what they look like. Okay, so how does this test, what's the experience of this test? So this is the first just sort of case series. So it's what it is. It's just a case series. We were just asking the question, once this test was approved by FDA and is now out there, and more people, it's been used now thousands of times, and we keep track of all the experience, but plus we have every single file. So 22,000 gene expression and all this analysis. There's a lot that we can go back in to relearn and relearn and relearn, depending upon the information that comes in. But this was first just asking, how are people using this? So, you see totally the limitation. It's some people are choosing this because they have uncertainty. And, but that uncertainty came turns out in 2 forms. One where there was a presumptive diagnosis, but there was some reason to be uncertain. And we've not tried to quantify what does that mean. Why did you order this test? But what we did know is that the intention was to treat as if it was that diagnosis. And basically, in the first 300 cases that we looked at, when this was first getting out there, 36% of those 300 cases, there was a specified primary site, and in 64% there was not. It was called CUP. As this was like a year ago, as more and more people use this ratio is more like, it's looking more like 60-40 or 55 CUP and 45. It's just sort of changing. And why is it changing? It's changing because of the feedback that physicians are getting. And first of all, in this group, when the ICD-9 code was, non-specific primary site, 95% were given definitive diagnoses. And we can talk about what does that mean to say this is a definitive diagnosis. Is it real? I mean, we can talk about that. The primary site, so in this first series, 57% of the presumptive diagnosis was changed. 57%. And this is really, when physicians do this, they have this experience and, and they change their treatment. We can talk about, does that make sense for them to change their treatment? What's the basis for changing your treatment? But 57% of the time, when physicians have a presumptive diagnosis in metastatic disease, in this total just random case, there's obviously uncertainty. We'd love to know for all comers, for everyone that comes into a particular set of centers or offices with metastatic cancer, and we're now doing this study. If you look at everyone, how often, why do we come to a particular diagnosis? And you really go back to this. There's no standards. IHCs, as I've told you, are unbelievably unstandardized. It's judgment. It's all sorts of judgment. You put it together. If you talk to the pathologists, there must be pathologists here, especially when we first went, we took it to pathologists at major centers. They just said, we don't need this, because we always know what it is. And we said, well, we'll give it to you for free. Just try it. And then Memorial Sloan Kettering now, they said, we don't need it. Now uses it for all their tumor boards. And it's a very interesting thing to experience, this sort of thing. And the result of that, so this was the change of diagnosis. And this was the change of therapy by now accepting that if this rules in ovarian cancer and rules out everything else, if that's good enough to accept that that is ovarian cancer, and the company doesn't tell the docs what to do. It says this is what we know, this is what it is. We haven't come across anyone that doesn't say, I can no longer treat this as if it was pancreatic, it's ovarian. And so it turns out in 63% of these almost 300 cases, a major change in therapy was initiated. And these changes relate to surgery, radiation, and chemotherapy choice. Minor changes in 18%, no change of therapy only in 19%. And I actually find this quite striking. This for me with the following the director's challenge. This is very exciting. Here feels like a molecular diagnostic that has this very rapid, when you experience, impact on behavior. We are now doing a whole variety of other studies to try to get at, does this sound right? Or is it right? It's an incredibly difficult thing to think about. Are we supposed to do a randomized control trial? Should we postulate that there is something biologically different about a tumor that a particular pathologist someplace is uncertain about versus certain about? Is there a different biology of not having found a primary? Or is this just an observer issue? It's very easy to know how to change the number of unknown sites of origin is just do fewer tests. You look less. That's flippant. But to me, this is a really fundamental and interesting question. We can hypothesize with no basis whatsoever, but we can hypothesize that how you find something is in some hidden way, a reflection of fundamentally different biology. And then we would have equipoise and say, we should randomize these people. We cannot find anyone and we've been working for over a year to figure out an ethical design for randomization. I think it raises an incredibly interesting question about randomization as this holy religion as we impose biologic knowledge, which can't keep you with equipoise, right? If you really know a lot about something, do we really aspire to equipoise when we know more and more and more about biology, and then say you can ethically randomize people because you will pretend you don't really think that knowledge is of any value? And I think this is a huge issue going forward if we actually are ever going to be successful at science-based medicine. We're going to challenge equipoise, and we got to figure out, when do we do randomized trials, when does it make sense, when does it not? And so there's a lot of things you can do here to ask this, but I think one of the most profound and intriguing questions here, first of all, that I think you can say that there is no bright line between someone's uncertainty and a decision to say it's unknown. And what I will tell you is that the fraction of tumors that are unknown today is very different than the fraction before imaging. So now, this could tell all of those things. And so this issue of whether at any moment in time the things that our tools don't find, does that imply a distinct biology? That's what has to be implied by wanting to know, but should you make a decision? Should you treat something that has a complete gene expression pattern of, say, testicular cancer, and has no gene expression pattern of, any other tissue you look at? Is it a reasonable equipoise hypothesis that is not testicular cancer, that it was some very interesting transdifferentiation of losing one, and there's you can hypothesize that, but I think this is part of what's so, to me, really fascinating about the questions that arise with this particular test. My own view is that, I know this sounds ridiculous, the clinicians here, but I get a lot of phone calls of people think that I'm a real oncologist about, referrals and things like that. And I'm really good at calling people, which is what I do. But I've had the experience myself of using this test, and it's anecdotal, but it's a very interesting. I've not seen a test as much that when a physician uses it, the number that reorder it, that use it again, not on the same patient, that come back and do it. It's just absolutely intriguing to me, and I actually think it's very exciting. But the point of this story is how hard this was, and it took a year and a half to work with the FDA, and actually they were terrific, but they'd never dealt with these sorts of analytics. They didn't know how to think about multidimensionality data sets. This has not been done. And it was really good working with them, but it was a long slog. This every aspect of taking this from this idea, this low-hanging fruit director's challenge to something on the market is remarkably hard. But I actually end up as I'm glad I didn't write that article for Nature. I actually think this continues to really encourage me. You learn how hard things are, but I actually think that the oil we were all selling and have been selling, there's real stuff there. What we're going to be doing is a head-to-head between IHC and this, and the question is, why would you use IHC, at least to know the tissue of origin? I mean, it's just, why would you do an unrigorous, unvalidated measure of one gene expression, when you can, you have a validated test and get an answer quickly. I mean, it's a really extraordinary thing how, many of you have taken care of patients that have the conundrum that you can't tell them what their tumor is. It's an enormous psychological burden, them, the family, very, very difficult. And I actually also think that there's real reasons. But the biggest thing still is this question, how do we know how often the diagnosis of a metastatic cancer is actually correct? I think this is I had no idea that it was going to look like this. The more we do this, the more it confirms that there's a lot of uncertainty out there, but there was never a good way to resolve it. And you don't get at these answers without having the tool to do it. So that's the talk. I think there's reasons to be quite optimistic, but also reasons to be sober about again how hard really great translation is. That's all I have to say. Thank you. Lee.
I have two questions. One, which would be, have you ever been able to sample a few of your already now people about it? Say, well, how do 12 cells read something from it? After you guys know it.
Oh, I mean, so
Repeat the question.
So the question is, if we know it about this, so we've done this, we've done this trial, we've done the 6, and there's for these cups, there's what you tend to get. It's complicated because what you really tend to get the answer is that we're not going to make a call. We think this is either this, or this, and you get sort of so you get this. And there tends to be a fair amount of agreement about this is one of 3 likely things. And we don't have enough data, but what I would just say, what it sort of looks like, for certain of these answers, it usually is one of those 3. But for other answers, actually, it looks almost random. And these are, these are very good pathologists. I think it's for good reasons. You can't tell.
My next question is the issue of equipoise. So, I was talking to you yesterday. I think the Plexicon study is the most unethical study I've seen in my time as an oncologist. What about the issue of using Bayesian knowledge in a phase 3 study? At least that then uses ongoing accumulated data to not keep randomizing in the same way if you get one field. Has that been explored or discussed?
Well, people are discussing that quite a lot. I mean, the Plexicon issue. I mean, I don't want to. I have nothing to do with the company. I don't want to defend it. But what I do know was the choice they made, and I said this to you, was out of anxiety about the FDA. And even though there was guidance to suggest it didn't have to be done that way, the cost of suddenly coming to the FDA and saying, "Oh yeah, we gave you that guidance, but that was, but we really would have rather seen this," and so it's it makes for very, very super conservative decisions, which is a shame. But Lee, I totally agree that we need fundamentally different designs, and I actually think that the whole point of science-based medicine is to drive us towards N of 1 trials. And that ought to be our goal. That's right.
transcript, so that didn't take into account related to that. And now look at the outcomes of the patient whose treatment changed
Yeah.
as a result of the prediction.
Yeah.
How does that work?
So there are two things. One, should this be further evolved and informed by, say, microRNA expression, and it's being done, and we've been working in collaboration with Regulus for that. And it'll be interesting to see, because again, with these type of predictor, it's, again, because it's not about whether we're at the mechanism, but we're at just what does it take to prove robustness of your fingerprint or something like that. So it's a very interesting question. I don't know, but we're going to try that with the microRNA. Now, Dina also asked, well, okay, so what happens when you change therapy? Do patients do better? And I wish I could tell you, but of course, all I can possibly tell you would be anecdotes, and I can give you some anecdotes. But I mean, but the problem is twofold. One, we're now, and this is really interesting, so what do we know about best therapy? We know about the group behavior from trials, the group. We have no ability to know what any individual response would be from that. And so the problem here is that now we are switching from group-generated knowledge to asking what happens to an individual. And the problem is you would have the same, it's a very interesting thing, you would have the same problem without this. If you actually ask the question for an individual, that instead of treating, which we would never do randomization of randomization, because we've never done that. We've never actually taken all possible therapies and randomized them against all possible tumors to actually see that if you treated, a pancreas, or, a breast cancer of this stage with an optimal therapy for stage 3 colon cancer, we don't have that sort of data. And so this is so to imagine a trial of outcomes would be just enormous. This is a real problem. I'm not justifying it. It's a conundrum for us because we actually want to know that. And so we have a registry that's all IRB approved and everything, where you look at, a whole variety of measurements of, and we're actually trying to design a trial where you look at, response rates, where we know the answer, but we don't give it to the patient, to the physician. We've designed this, but it's not clear when we talk to physicians. They don't want to do that. They actually come back to us and say, well, why would you They would tell us we wouldn't feel comfortable randomizing. So we're really having trouble getting the answer to that. I mean, it's sort of amazing. One of the reasons I've gone different places to give this talk is I've given it to throw it open for help us design trials to test the value of this. I had just really wonderful discussions. These are quote seminars that go on for hours because and it's fantastic, and there's been lots of ideas, no clear answers for the outcomes issue, but boy, we'd love to know it.
Rick, one issue is how much information is embedded in the microarray results. So for a specific tumor type, is there enough heterogeneity for you to be able to say, this tumor is going to behave in a certain, if you had the clinical data, this tumor will behave in a certain way, will respond well to this therapy, but not that therapy, and so on. Is the microarray data sensitive enough and specific enough and accurate enough to go to the higher fruit on the tree? Well,
we're hoping. That's why we developed this, and that's why the data files on every patient is not the two. So there's only 2,000 genes in the end for the test, but 22,000 are measured. We have all that because we want to be able to accumulate that, but the limitation of that is just what you said. What outcomes do you measure, and what's your cell size? I mean, how do you determine heterogeneity, and then how do you put that in a cell against therapy to know that it's an actual correlation? And this is the personalized medicine conundrum.
Yeah, I was wondering, in your breast cancer, in the patients with CUP who are diagnosed with breast cancer, how many of those patients express hormone receptor or HER2, or are these just poorly differentiated sort of triple negative basaloid cancers?
This is a question we haven't finished looking at, but it was my question to the team. I was really interested in that. And so I don't have an answer. But so far, the data that's coming out, this does not look skewed. So we can read, of course, you go back, and we've been doing that. We can go back and read gene pathways on individuals. So we know whether there's ER there and whether there's an ER transcription pattern. And by the way, that's not the same as the ER being there. And and there's actually a very interesting relationship, it looks to me, about ER level maybe and whether you have an ER transcription pattern, and it's not obvious. That it doesn't go in the way that more is more. But so the answer I'm giving you may turn out to, when we do the full analysis, totally wrong, but to date, when we've looked at that, we get all types of breast cancer in the cup. I think...
So you've picked an area of oncology which is one of the most difficult for determining therapy, whether you knew the tissue or you didn't. These are people that are being referred to you for precisely that reason. I'm wondering, why not pick an area where the prediction is better and the pathologists think they know for sure what to do, but they may be wrong? And that would be to do your test on somebody, let's say, with breast cancer, where you think you have a very high predictive value from pathology, and maybe they're wrong, and follow them and find out. That's one choice. The other is to go back and look at the primary tissue from these people with metastatic disease and do the test and see if it changed.
Oh, so we've done that. So that's been done, and there was basically no change.
There was no change.
Right. The problem, if you're asking, why don't we do it with, say, primary breast? Because actually, I think, when you have a primary and it's in the breast, the chances that it's a metastasis to the breast. So this really is an issue, I think, for metastatic disease. But not all metastatic disease is totally untreatable. You now see some really big differences in responses for certain types of cancers, testicular, ovarian, others.
In primary breast, there's a significant number of patients that don't respond the way they're predicted to.
Oh, I see.
And maybe the reason was that they weren't really what they thought they were. That was my point. Could you identify them better than the pathologist?
Yeah. I mean, so I do think, and this has been done by many other people, I think there's no question we can better identify meaningful subsets of, and breast cancer is probably the best example. I don't know that we know how to do it for, say, colorectal cancer. I think lung may turn out to be the next one, where, you absolutely can determine much more that's relevant to response from gene expression, whether it's array gene expression or high dimensionality expression, or the mixture of high dimensionality with very specific pathways. I think that can be done, and that's really the next phase of what this company is doing, is adding on absolutely specific pathway measurements for each of these. So it doesn't stop with this. This was simply the entree, and it was just unbelievably hard to get this far. Now, the bar, is lower to do all that next stuff, which is what the company will do now.
Hi. You mentioned transdifferentiation, and so my question is, what about those, that set of cancers that have just lost all the signature of their original primary? Is it possible that that the knowledge that it came from something else is almost irrelevant, and you should go with what it is now, or have that kind of
really
question? How do you deal with it?
One, I don't know that we have an example of a cancer that we know at any point in its metastasis, evolution, clonal variation, loses all signature of its origin. I mean, it's not that I can't imagine that, but I don't know of a documented example of that. And that transdifferentiates to take on, so I think we'll need to deal with that if anyone actually finds something like that. But I could be corrected, I don't know of an example of that.
But that would be the tumor that you couldn't figure out what it was.
Oh, yes,
right,
yes.
course, yeah.
And so one of the things that we're actually now going back and doing is when you take CUP, let's say true CUP from really great centers that's done everything, and the ones that don't give a signal for any tissue. So, and that's actually what happens. It's not that, well, you get 3 signals, and so you can, you can definitively rule out everything on the panel. Now, there are things that are not on the panel. Endometrial is not on the panel. Head and neck is not on the panel. Neuroendocrine are not on the panel. So those things could be added. It'll be interesting to know, can we, with just the full set of rare tumors, can we get all of them, or will we end up with some fraction that are, stem cell tumors?
Could I ask you a quick question? I'm not an oncologist, but it's time to get educated and perhaps build some confidence in the ideas and approaches you have expressed. Now, let's take it that 50% of the time, the original diagnosis needs to be changed. It turns out to be wrong. And let's assume further that the treatment was instituted based on the original diagnosis. Now, what will be the prediction of failure rate of such a treatment? Does that jive with the reality as it might exist today?
As I said, we really don't have those numbers. I mean, we do not have numbers of the failure rate or, quote, the wrong regimen, a regimen that's not standardly used and not has been tested in a particular tumor. So, and again, on top of all of that, so we don't have the data by which to predict it. And secondly, we are dealing in this case with patient by patient. And so we are, even if when we have this data, we're extrapolating from group behavior, from clinical trials and randomization, to individual behavior. And that's a very tricky thing. All you can assign is a probability. And without numbers, you won't know whether the probability would be consistent with a patient being cured of something and, versus, being made worse. I mean, that's, and it would still fit with that the group prediction is right, but you just have to have enough individual patients to see how their outcome distributes. And that's really the big problem here. It is the interface between, how we've come to understand response in at least for traditional chemotherapeutics. It gets very, very different once we're talking about, molecularly targeted therapy. And then it becomes a totally different patient stratification. That's, but I think that's not the question you're asking.
Thank you.
Okay, so let's thank Rick for a terrific, stimulating talk. And there will be a reception in the atrium behind the amphitheater, so if you have additional questions, you can ask them then.